All right, so this problem says this is another classic calculus problem that is going to be in every practice test we do. Every AP test is going to have, our midterm final, going to have problems like this. A particle moves on the x-axis. We call this particle motion problem. Particle moves on the x-axis in such a way that its position at time t greater than 0 is given by the function x of t equals da 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 da. For which values of t is a particle moving to the left? So, when we first started talking about derivatives, remember the Bismarck problem? Remember the car traveling east and west of Bismarck, right? We first introduced derivatives. That is a particle motion problem. Okay, one-dimensional motion is classic, position, velocity, acceleration stuff. So if this is Bismarck, east of Bismarck means to the right. That was positive, right? So 1 mile east, 2 miles east, 3 miles east, 4 miles east, right? And then west of Bismarck is negative, right? Negative 1 mile west, 2 miles west. And so if you're traveling west, that's a negative velocity. If you're traveling east, that's a positive velocity. Well, so we could talk about this motion from Bismarck or someplace, but a really easy way to do it is just talk about the x-axis. So the particle is now the car, and our interstate is now the x-axis, and you just have this, right? So when we say a particle moves on the x-axis, just think of a car going east is positive and west is negative. Make sense? And so that's all those kind of problems are, okay, whenever you hear them. But what it does also introduce is, remember yesterday I said, and I knew this was coming, this is why I wanted to do this today. Remember yesterday when I said, when we do a differential equation, we can tell the output variable because it's the one that has the prime on it, right? So if I give you an equation, if I give you a differential equation here that's y prime plus 2x squared minus 7y double prime equals 0, that's a differential equation, right? The input variable is x, and the output variable is y, right, in this function. And so what we're trying to find is the original function. So we're trying to find y equals and then a bunch of x's, right? I mean, that's what we're looking for, the original function. Now, we wouldn't be able to solve one like this. All we would be able to do is do a t-chart and maybe verify that some y was the solution, right? Okay, so we were talking about that. And one of the comments I made was we always have the prime on the output variable, right? Never on the input variable. We never see x prime. Well, and then I don't know if you remember, but I said we never see x prime. Well, we haven't yet. Well, in this problem, and then so if you did this problem, you have, right? Because what's the output variable in, not this problem, what's the output variable in this problem? X. What's the input variable? T, the time. So if you did an ordered pair for this function, say you did, I don't know, 1, what would 1 be? 3 negative 22 plus 60, what would that be, 38? That would be an ordered pair on that function. What would that mean? Well, the 1 would mean what? That'd be t, so let's make up something. Let's pretend it's a car. 1 hour. At 1 hour, the car is 38 miles east of Bismarck. Now, we wouldn't usually write as an ordered pair. We write it this way. X of 1 equals 38, right? And we'd say at 1 hour, it's 38 miles. So it is not unusual for us to have a problem in calculus where x is the output variable. These particle motion problems, x is usually the output variable. So it's x of t. So because the output, so the time is our input and our output is where we are on the x-axis, our position. Okay, so that's, I think it's 37 or 38, 37 in your homework have that, right? Which makes it a little confusing if you're not used to that, right? X is the output variable. Now, to finish out this problem, so this is just a really good problem. So it says, when is the particle moving to the left? So what are they asking? When would this be moving to the left? When it's what?
Negative.
When what's negative? Not F prime though. X prime, right? The derivative, when the derivative is negative. And if you think about it, what that means is its position is decreasing. Because if the car's going left, and so this is why it makes sense to use west as negative. Because when the car is moving to the left, what's its position doing? Its position is going from 4 to 3 to 2 to 1. Those are decreasing values, right? So when the particle is moving to the left, the position is decreasing. X is decreasing. And so therefore, X prime would be negative according to the chart. So this would be as simple as, and maybe nobody had a question because it was just an easy problem. That'd be awesome. Okay, but it would be something like this. Okay, and we could certainly take out a 15, would make that way easier. We would be setting that equal to 0. We'd be wanting to do a number line. Okay. This would be t squared and t squared. This would be what? 4 and 1. Minus and minus. So what's that going to equal right here? Plus minus 2. What was that? T is plus minus 1. Now, of course, this is time in this problem, so time they told us was positive, so we can ignore the negatives, and we just got 1 and 2. Now, what does that 1 and 2 mean? In this context of this problem, in the particle problem, what is the context? What is happening at 1 and at 2? The particle is stopped, right? Now, what might happen when it stops? It might turn around, but it might not. It might stop and keep going. How would we tell if it changes direction? Would be a great way to find out. Number line, right? Sign analysis. Do a number line. So a particle problem is just like a local max-min problem. It's chart stuff, right? It's chart stuff, but with some context to it. So yes, we would want to do a number line on this, not this number line. We wouldn't even draw this number line if we're doing the problem. I just put it out there so you have a particle moving on the x-axis is what we're talking about. But we would go 1, we would go 2, we would put some numbers in here, okay? And we would probably plug them into here, would be the easiest. So put it as 0, that'd be negative, negative, that's always positive, so that'd be positive. Put a 1.5, what's 1.5 squared? Even if you don't know it, is it bigger or littler than 4? 1.5 squared is littler than 4, so this is going to be negative. 1.5 squared, bigger than 1, so when you subtract them, that's going to be positive. So we're going to have positive, negative, positive, so that's going to make it negative. 3 squared, that's going to be positive. 3 squared, that's going to be positive. So this car is going, this particle is going east or right, left, right. Yeah, I mean the car would be east, west, east, but the particle would be right, left, right. Okay, and then of course the question is, when is this particle moving to the left? So between 1 and 2, between 1 and 2. Okay, but if you just look at it, it is exactly what problems we've been doing with local max-min. Right, it's the same exact thing, same exact thing. Okay, all right. Instead of saying when is the position, when is F? The questions I've been asking is when is F increasing? When is F decreasing? Right? Well, asking when this particle is moving to the left is like asking when its position is decreasing. Right? It's the same question. Okay. All right. So that's just that's how we do chart problems a lot, or that problem shows up a lot in these just in calculus problems in general. So just understand it fits right in with what we're doing. All right, so let's go ahead and look at some of the questions you had on the homework, and then we'll kind of summarize where we're at as we take towards Tuesday's quiz, because like I said, we don't really have much or anything new to really talk about other than getting better here at what it is and making more sense of what it is we're doing. All right, so let's start. Well, let's just start with number 6. So I've got a couple in mind here that I want to I want to talk about. Now, I helped you yesterday, so one thing we got to make sure we're understanding is where we put, when we're doing these verified problems, where are we doing this? Where do we put the T, where it's useful or helpful, okay? And we're told that y is equal to the square root of c minus x. Now, was that negative?
Yeah.
Am I missing? That's supposed to be negative? And then this is right here, for part A anyway?
Yeah.
For part A. Okay, show that this is a solution. So, now, of course, we would probably write this c minus x to the 1/2. So I'm going to put that right down there. So I'm going to put that right down there for the y. And then for the y prime, I got to do the derivative of that, right? So I'm going to bring down to 1/2, c minus x, drop that to negative 1/2, correct? Not correct.
I got it, so, but they didn't end up being equal.
They should be, because my derivative is not correct.
We need to kick out the negative one.
That's the tricky one, right? When there's a number multiplied times the x, we have to kick it out, and there is a negative 1 multiplied by that x, so we have to kick out a negative 1. That's the easy one to miss. When it's a 2 or a 3, we usually don't miss it, but when it's a negative, we sometimes miss it. So that's negative 1/2 c minus x to the negative 1/2. Now, another little point I want to make here. Do not leave these like this and say, hey, yeah, it's a match, because they don't look exactly alike. Now, you can probably in your head do a step or two and tell, oh, yeah, these are going to be a match. But I want you to show it on your T-chart. I want you to show that they are exactly alike, so you could show it to some 9th grader who doesn't know anything about calculus, and they would say, oh, yeah, those two are the same. Okay, so what you have is a negative power, which means it flips to the bottom. So the 1 would stay on top, the 2 would stay on the bottom. This would flip down, and then sure enough, those are a match. Okay, so that's what 6a would look like. 6b says, is negative square root also an answer? And what you get, well, what would change here? Let's put it in red. If that was negative, we would do the same derivative, but we have to kick out a negative, so wouldn't this turn to positive? So over here, this would be positive, and this would be positive right here. But then what would change here? When we put the y in, right, on the bottom, wouldn't we have a negative down here then? And then those two would cancel, and it would still check. So there's two solutions to this, and that's not unusual for differential equations. What you'll find out is we often have different branches of our original function solutions. Not only vertical shifts, we not only have vertical shifts, but depending on our initial condition, Maya, as Maya pointed out to me, I forgot to tell you guys yesterday what this is. Okay, some of you may have seen that in the homework. The section 2.6 problems. An initial value problem is what that stands for, initial value problem. And like it says, it's got an initial value. All that is a differential equation plus an initial condition, like all the abbreviation. It's just a differential equation with an initial condition added in. Remember we said that when you do an antiderivative, which is kind of happens sometimes in differential equations, we have to do an antiderivative because we're going from y prime to y. There's a whole vertical shift. There's a whole bunch of different possible solutions, the plus c part of it, right? Well, if I give you an initial condition, if I tell you one of the points on the original graph, that locks it in, and then you just have one solution, not an infinite number. So that's called an IDP. So when you see IDP, it's differential equation. That's all. It just means they've added in an initial condition. All right. So I had that one down to look at. Anything else on that first section on 2.5? Anything else in the 2.5 section you want to look at? I mean, there was a bunch of them where you had to verify the solution. Anything? 25, Haley and I were talking about, was that 25 we were talking about? On 25, and again, this is where the, and Haley did something that is very, very common where people do this. Because I told you, it's not like you have to do the T-chart to verify something's a solution. Okay, so anytime it says, is it a solution, show that it's a solution, verify that it's a solution, we're doing the same thing. So here's a differential equation, here's the solution. So we're going to plug x squared in here, right? Now if you don't do the T-chart, so here's what she did. So she did, and I'll pick on her here, but it's just classic way of doing it is you say, okay, here's your y prime, y double prime, so you start plugging them in. So you get 2 minus 4x times y prime plus 4 times y. This is all good stuff. It was, when she did it, it was just perfect. And this was all good. Plus 4x squared, was it like that? And so far so good. And this would be 2 minus 4x squared equals 0. And then when you're doing this, what do you just feel like doing next? Solving it, right? You feel like adding the 4 or subtracting the 2 and getting the x by itself, right? And that's not what you want to do at all. That's not what you're doing, right? Really, you're now at a stopping point, right? You would now stop and say, no, it's not a solution because the left side doesn't equal the right side. And that's what I like about doing the T. If I would have in the beginning done this, right? In the beginning, if I would have said this, then that would kind of prevents me from wanting to do that. And that's why I like it, okay? So it just feels like now I'm not trying to solve something. I'm trying to see if the left side is equal to the right side. That's what I'm trying to do. Okay, so that's what I like about the T-chart. It just keeps me from wanting to solve an equation, because that's not what we do. Okay, so we say, no, those two are not the same. They are the same for some value of x. There is some value of x where they are the same, but that's not what we want. We want them to be the same all the time, right? All the time. So that's why we want the two sides to be equal all the time, not just for some value of x, because there is some value of x where this will work, okay, where those two will equal, but that's not what we want. All right. Okay, what about 43? Wasn't 43 one we did? This is probably something you're going to have to do on the quiz. Okay, the two big things you're going to do probably for differential equation, well, maybe three big things. We'll get into the third one in the next section. Verify that something's a solution. Probably get to do that a couple times. And then this right here, number 43. Express something as a differential equation. I want you, because one of the things I told you yesterday is one of the values of differential equations for engineers and people, right, using calculus, is it can model situations that involve changing quantities. Okay? So, when we have the sentence, the rate at which the temperature of an object changes is proportional to the difference between the temperature T of the object and the temperature S of the surroundings. Express this physical law as a differential equation. Okay, so let me say it again. The rate at which the temperature of an object changes is proportional to the difference between the temperature of the object and the temperature T of the object's surroundings. So, T is the temperature of the object. S is the temperature of the surroundings. Now, where we usually, what I usually think about this would be a cup of coffee sitting in a room. So the coffee is the object, and then the room temperature. Okay? Now let's assume the room temperature is constant. The room temperature is not changing. Okay? So now let's see, does this make sense? And when we say is proportional to, what do we mean?
Just K, because like you multiply K.
So as one quantity gets bigger, the other gets bigger. Or as the other one gets smaller, the other gets smaller. So by some proportion. And that's the K value, right? We talked about that with the bank interest yesterday. So, what would we write for the rate that the temperature is changing? using those two letters right there. What would be the rate that the temperature of the object is changing? T prime. T prime. So the rate that the temperature of the object is changing is proportional to the difference between the temperature of the object and the ceramic. See how I write that? See how easy that is to write? I just read those words and I write. So you first have to identify your variables, where the rate is in there as a prime. That's a differential equation, right? S is not a variable. In this case, S is just a constant. Now, doesn't it make sense? Because what this is saying is the bigger this is, the bigger this is. Right? Well, what does it mean if this is big? What does it mean if this is big? T minus S. Think of the coffee example. No. I don't care about that right now. What does it mean in the coffee situation if this is big? There's a huge difference in temperature, right? The room's really cold and the coffee's really hot. If the room's really cold and the coffee's really hot, this is big. And then what does this being big mean?
It's going to cool down fast.
It's cooling fast. The rate is fast. It's going to cool fast. Well, doesn't that make sense? If it's really hot in a really cold room, the rate that it cools is going to be fast. But if that's not very big, that means if the coffee temp is about the same as the room temp, it's not going to cool very fast, right? It's going to be an exponential thing. This actually has a name. This is Newton's law of cooling. This is the other one we're going to memorize. Remember I said there was two different equations we're going to memorize? This is the other one. This is called Newton's law of cooling. The rate that an object changes temperature is proportional to the difference in the temperature of the object and the ceramic. Okay? It makes perfect sense, and it's really easy to write. Here's the problem with it, and this shows the problem with differential equations to use, is what if I said after 5 minutes, how hot is the coffee? Where would you plug in the 5 minutes? You need little t. There's no input variable here, right? This is our output variable, right? Right? The thing that has a prime on it's our output variable. That's our output variable. This is a constant. This is a constant. There's nowhere to plug in the 5 minutes, right? What we need is the original function, big T, right? We need big T equals da-da-da-da-da with little t in it. How hot is the coffee at a certain time? We need to solve this differential equation, because solving it then gives us a function we can work with and tell some stuff. So it's a great way to very simply represent physical situations. It's just not a great way a great thing to use to find out things about that situation. So we need the solution to this differential equation. Okay. Anyway, you need to be able to do that in words. Okay, that's one of the things. So we'll have some other ones we'll practice. Okay, let's turn to 2.6. Any of them there? We had 11. We had 37, 38, 47. $37? Oh yeah, that was the one I was talking about earlier. Okay, so it says x of t equals ln t. Okay, now again, at the end of the day, when we look at this, we're going to think, man, that was easy. Okay, but it is about getting used to the language and what's going on. So this is position. Now remember, we have position, velocity, acceleration. So this is position in meters. Now the x makes more sense, maybe the position of the particle, right? X is our output variable. All right, is the name of our function, our output. Find the average velocity over the interval. I've told you this year, when you hear average, average means what? Slope between 2 points. Average rate of change. That's what we're talking about. Velocity is the rate of change of position. Average velocity, we mean slope between 2 points. Well, what are the 2 points? 1 and E. So for part A, we immediately go, now this is what looks weird, x of E minus x of 1. Now hopefully now that doesn't feel as weird now that we've talked about this a little bit. X is our function. So it's just like doing f of B minus f of A over B minus A. That's all it is, slope between those 2 points. But the function is x. Okay, so our input is t. So what's x of E? It means put an E right here. What's ln E? 1. Put a 1 in. ln1 is 0. 1 over e minus 1 meters per second, right? That's it. Okay, it's just getting used to the language of functions and everything else. Average rate of change, average velocity, that means slope between 2 points. Okay, but what's instantaneous rate of change mean? Slope at 1 point, which is what? Starts with a D. Derivative, right? Instantaneous rate of change is the derivative. That's what it is. Instantaneous velocity would be the derivative. So that's x prime of t. Well, what's the derivative of ln t? 1 over t, right? Now, we wrote it as ln x, but it doesn't matter. Now we're doing the derivative with respect to t. Yesterday, I had those written up here on the board, right? Derivative with respect to x of ln x is 1 over x. But I just as easily could have said derivative with respect to t of ln t equals 1 over t. Derivative with respect to German short hair of ln German short hair is 1 over German short hair, right? The variable, the input variable could be whatever. It's usually x or t, but it could be whatever, all right? And in differential equations, it's t a lot because we're usually talking about things, rates of change that involve time. So it often involves time, and so t is used a lot when it comes to differential equations. Anyway, this is 1 over t, so the derivative at e would be 1 over e. Right? Okay. So, the language. What else? What else do we have? 38, well, it's the same thing, right? Be 1 over 2. 47.
Wouldn't
Do that.
X double prime?
What's that?
It's acceleration.
So x double prime would be acceleration. Okay? So x prime is t to the negative 1, right? So x double prime would be negative 1 t to the negative 2, or negative 1 over t squared. Right? Why, is that what the next problem was? Oh, yeah, I'm sorry. Yeah, you're right. I'm sorry, I totally misread it. Oh, who was I helping this morning? Is that you? I'm 38 and I said it'd be 1/2. I was wrong. No, it's not 1/2. I didn't see the word acceleration. I'm 38. I totally misread that. 38 says find the instantaneous acceleration of the particle. So yes, so that would be the second derivative. Yes. So you would do that, okay, and then you would plug in your 2. So it'd be negative 1/4. Negative 1/4. Yes, thank you. Okay, so x double prime is acceleration. All right. 47. Let's talk about 47. Okay. 47. Because this, so I said there were 3 things that we would probably have to do with differential equations. Verify something's a solution. Be able to take some words and translate it into a differential equation like that last one. And then this one. Work with, if you remember what we said about differential equations, we said there is the type we can't solve, but we can memorize the solution. If that's the only one we're going to memorize is this one right here. Output variable prime equals k times the output variable. So p prime equals kp, y prime equals ky, z prime equals kz, whatever. The solution is always this. Well, those are either going to be some sort of population growth or some kind of exponential growth or decay or bank interest, right? Well, that's what 47 is. So 47 says P prime, so the bank has 8% interest, and that is fulfilled by this differential equation. Okay? So what you do, as soon as you read that, you know that the solution to this is A, E, what's K? 0.08 T. And you know that because this is the differential equation we're memorizing. That is y prime equals ky. P prime equals kp. P, where the K is the 0.08. So we now know this is our equation that we will work with. So again, it's easy, it's the only one. So if you get a problem on the quiz that's about bank interest, or it's about some sort of population growth or something like that, it's AE to the KT is the equation, and it comes from that difference equation. We just automatically go to that, because that, we've memorized that as our solution. All right, so what do they say? $2,000 is initially invested. So what do we put over here? What does P stand for here? What's P stand for? The value in dollars after T years. So initially, $2,000 is invested. So where do I put the 2,000? No. Well, okay. Yes, but that's only because it's at time 0. I could give you a problem like this. What if you put, and you can do it, if I gave you the problem, said your grandma gave you $2,000 when you were 5, how much is it worth when you're 25? Now you can put the 2,000 in for the A. What would you put in for the time then to figure out how much it's worth? 20 years, because from 5 to 25 is 20 years, right? So yes, you could always do that. You could always manipulate it so that your beginning amount is A. But I would like to do it. I want to show you this, because the the 2,000 is P, right? The 2,000 is the amount in the account at time 0. Now you're right. I'm being a little picky about it, because what would I put in for the T right here? 0. And then what happens to this? E to the 0 is 1. So the A is 2,000. That is correct. Now, but it's only true that the A is 2,000, okay, when time is 0. Okay? So that, and so if you jump right to that, that's fine, but just understand the consequences of that. Because if you then wanted, so it says when you're 5 years old and you get $2,000 and that goes into your account, how much you have at 25, the danger is you put the 2,000 in for the A and then you type a 25 in for the T. And that would be wrong. That would be wrong. You'd have to put a 20 in. So as long as you make that adjustment, that's fine. Okay, so how much is there 10 years from now? So you go ahead and put a 10 right there. Okay? Like so. All right? And well, I wasn't going to talk about this right now. Remember the Newton's law of cooling we just talked about a minute ago? The solution to that differential equation is this. If we use T, big T for the temperature and little t for the input, it's this. That's the solution to that problem. The surrounding temperature plus AE to the KT. Okay? Now, if I tell you that the initial temperature is 180 degrees of the coffee, does the 180 go in for A? It does not. Right? So that's another, that's a danger. I just don't want you to think that this number here is always the initial value. It's not. Okay? The 180 is the temperature would go here. The 0 would go in here. And so you'd have S plus A equals 180. So you'd have to subtract the room temperature. And then that's what the A would be. So later on, that becomes a little bit of an issue if you're always thinking that this A is your initial temperature. Okay, so just something to keep in mind. All right, So, moving on. So those are the things we're gonna probably do with differential equations. So now let's talk about the global max min stuff. We had 37 and 44. So I don't know how much time I wanna spend on 37, because 37 is just exactly like the one we did in class. Now, we didn't do the number line part of it, but let's focus on 44. And when I wanna give you some work time here. So when we have some work time, if you've got some issues with 37, we can talk about it. Let's go to 44, because this is the calculator part. And put that in the calculator. So let's go through and make sure we understand what this looks like on our calculator when we do one like number 44. Okay? So again, as I read number 44, I see things like stationary point, decreasing, global max min, where's it concave up? So I mean, that's the whole gamut. That's going to need second derivative, first derivative. It's going to need the whole thing. Okay? So go ahead and you should log in that. Should be in it. I just started. Okay? So 44. We got 2 cosine x plus sine 2x. Okay, so since we got the whole gamut, and I could tell there, I might as well start by doing what? F prime equals 0, right? So here's where I want you to go ahead and use your calculator. Now, you don't have to use your calculator for this. Matter of fact, I'd rather you not. But I won't be able to tell. Well, I will be able to tell by the way you write it, because the calculator is going to give it to you different than you would do it, as you'll see here in a second. But what's the derivative of cosine? So this would be negative 2 sine x plus derivative sine, took out 2. So it's going to be 2 cosine 2x equals 0. And we can't solve this because of the 2. Now, there's a double angle formula you learned last year, trig. Whatever, we could get into that, and it actually turns out to be some nice points that would work here, but I'm not interested in that part of it right now, so I don't care about that. We're going to let the calculator do it. So Harish is go ahead and do the derivative for me on your calculator.
The graph or just like
The derivative. No, I don't care about the graph. Remember yesterday I said I don't want it. Now, is that the derivative or is that the original?
Oh, that's the original.
That's the original. Now, if you want to spend time doing that, I wouldn't recommend it probably in a problem like this, but if it's a calculator problem and it said where are the stationary points, where is it decreasing, where are the max and mins. Now, to be honest, if I was doing this, what is it, 0 to pi, is that our interval? So if you really wanted to graph it and make it useful at all to you, but again, none of this is going to be acceptable to get you points that you see on your graph. It's just there as kind of a double check, really. Okay? So what I would do, Harish, go back to the graph, go to your window, go back to your graph, go to your window, and let's set it from 0 to pi. And I don't know if I've shown you this yet, but there's something called Zoom Fit. When you have a set domain, Zoom Fit's a great tool. So go to your window, then are you not the presenter yet? I'm sorry. I haven't made you the presenter yet. Okay, go to your window. Zoom Fit is choice A, and then set your, you got to go to the window, not Zoom Fit yet, my fault. Go to window again, window Zoom, settings. You got to set your X and Y, or your X min and max, so go 0 and pi. Okay, hit OK, or hit enter, just hit enter. Okay. Now go Zoom Fit. Well, it's actually fitting in there nicely, but just go to Window, Zoom Fit. And what it'll do is it'll check 0 and pi and a bunch of points in between, see all the y values, and it'll fit your y's for you automatically, so it fits in there. So it's a really nice tool if you know you only want to look at a certain point. Well, now we know all kinds of stuff about this function, where it's increasing. We can see stationary points. We can trace. We can see, all kinds of stuff. But that's not the point, right? The point is the calculus behind what's going on. That's what we're doing. So I wouldn't, to be honest, on a quiz especially, I wouldn't spend time doing this, okay? I would go into doing the derivative. So go back to the calculator screen. So let's do the derivative. Now he could just type f1 of x, since he typed that in, save himself a little time right here, just type f1 parentheses x, because he's already got it stored in f1. So let's just save us a little time, hit enter. Here's what I meant by be able to tell if you did it on the calculator or not. See how it wrote it backwards from the way we have it written? So, but it's the same thing, doesn't matter, I don't care if you do that. But now, let's go ahead and solve on our calculator. So do a solve. Now this is where it's going to be really important to put the vertical bar in the 0 to pi, but I'm going to have him do it without that right now. So go up and grab that, go up and grab your derivative, okay, equals 0, comma x, and then just hit enter, okay? Oh, you didn't do equals 0, did you?
Oh.
Equals 0, okay, equals 0, hit enter. And then you're going to get, well, no, you didn't. I thought he was going to get his n pi stuff. But look at all this, -14, -9, none of those are in the interval. A lot of times what you get is, something n pi, blah, 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 and we don't want that, right? So go up and grab it again, and then do the vertical bar, and then go 0, 0 less than or equal to, no, 0 less than or equal to x. Everybody should know how to do this right here, because I can promise you on the calculator part of our next quiz, a Tuesday, you'll be doing some solving where you're probably, you're going to need, or going to want to have your calculator. Maybe it's a cubic or a 4th degree or something like that that you can't solve any other way. Okay, pi. It was just pi. Okay. All right. Now, it turns out these are actually nice numbers. It turns out that this is pi 6 right here, I think. I think this is 7. 5 pi 6. 5 pi 6. Arrow up. Arrow over a little bit. Is that it? So it's pi 6 and 5 pi 6 is what it ends up being. But let's assume we didn't know that. Okay, did anybody's calculator give them pi 6 or 5 pi 6? No? Okay. So so what you would do is what I would do if I was doing this is I would look at that. So what's that? 524 rounded. So 0.524, and what was the other one? 2.6. 2.6 what? 1.8. Okay, so there's my stationary points. Okay, so that was question A. Are there stationary points? Where? Okay, that's those. Where in the interval is f decreasing? So now I need a number line. So I got f prime, so I put 0.524 and 2.618. And then I need some other numbers, so 0 would be good. 1 would be good. 3 would be good. Because I'm going to use, now here's where using the other vertical bar comes in real handy, right? Because I want to plug in the other vertical bar, the same vertical bar. The other use of the vertical bar, 0, 1, and 3, I want to plug those back into the blue derivative here, right? Well, I've got it on my calculator screen. So right now, go up and grab that derivative. It was way up there. Or you could retype it, doesn't matter. There's your derivative. Now he can grab his derivative, do the vertical bar. Remember, no solve here, though. We're not solving anything right now. We're just plugging in a 0. Well, okay, we're going to plug in a 0. Now, we could have done that easily without the calculator. So that was a positive. Okay, then we're going to go back, and now we want to plug in a 1. And that is, better hit Control Enter. That's negative. And then we want to plug in a 3. So we're plugging those into our derivative. Now, if you want to type it in, 2 cosine 6 minus 2 sine 3, or whatever, just plug your 3 in that way. That's fine. You can do it that way, okay? But there's a positive. So all I'm doing is letting the calculator do the parts I was doing without a calculator before. If you're struggling with this at all, come see me in the mornings sometime, with your calculator. I'll help you out with it. So there we go. Now we know from the graph Harish had up there earlier that this graph's going up, then down, then up. Okay, so it's not surprising we see that. But the points you get is for doing this on your paper, having this shown, having this, and then talking about those things. So it says, where is f decreasing? Well, that's between 0.524 and 2.618. That's your answer there. Find the max and min values. Now, if that would have been local max and min, it's right here. So we would have said this is a local max. Since f prime changes positive to negative, f changes increasing, decreasing, blah, blah, blah. Local max means everything. That's not what they want. They want the max min values. So now we need list of candidates, right? So what does that mean? We want f of 0. We want f of pi, because those are endpoints. We want f of pi 6, and if you knew that was pi 6, I would put pi 6 because that's more exact. We're going to have a little issue with rounding I'm going to talk about here in a minute, okay? And then f of 2.618. Okay, now if you knew that was pi 6 and 5 pi 6, that'd be good. You could use those, but if you didn't, then here you go. All right. Now, I'm just going to write down 3 decimal places, but when I go to plug these in, so now here's where I can use the vertical bar with the calculator again, right? Except now I want to plug them into f, not f prime. So he probably needs to type in f. I'm not sure you have f up there anywhere. So f was what? 2 cosine x, 2 cosine x plus sine 2x. Now, to be honest, right here, another thing you can do, if you want to get into the calculator here a little bit, he can define f of x to equal that, and then he could just type in f of 0, f of pi, if he defined f of x to be this, right? And he wouldn't have to worry about the vertical bar, okay? So that would be an option too. But here we go, we got that, and then we want x equals 0. Okay, now that's an easy one, we can just do that on our own, right? Not a big deal, so there we get 2. Then he's going to plug in a pi. Okay, that's another one we can do without a calculator probably, plugging pi into those. But you got the calculator, so what the heck. Okay, what was that?
It was
-2. Okay, now here's where it gets a little tricky. Okay, so now I don't think it's dangerous to just plug in 0.524 here. Because if this is going to be one of our maximum values, it needs to be accurate to 3 decimal places. By plugging in 0.524, that may get some rounding error. It may not be accurate in the 3rd decimal place. So I usually like to go 5 or 6. So what is, go back up where you first solved. So where you first solved right here, 0.2, well, I don't know if you want to take all that, but 0.523598 is probably what I would put in. 523,598. Maybe jot that down yourself or whatever, but 0.523598. Okay? And maybe it's still going to be accurate, and maybe we would have gotten lucky and got away with it. So that was 2.598. Okay, and then put in that one. Okay. 617,993. 617,993. Okay, and -2.598. Okay. Now, it turns out, now go back to your graph screen. So it turns out that those are the max and mins, and it kind of makes sense. Those were the stationary points, and if you go back to your graph, sure enough, it went up for a little while, and so our max was at this stationary point, our min was at this stationary point, the end points were not the highest and lowest points. So it was the 2 stationary points, okay? So there is our max, right? And there's our min. Kind of lazy to do it that way, but what the heck. Probably should write it out over here, okay? But there we go. Now where is f concave up? Okay, so now we do f double prime of x. So Harish, finish it. We'll quickly finish this up. So let's go back to your calculator. We want to do the derivative of, right here. There you go. Okay, derivative of the derivative. So where'd you have the derivative up there somewhere?
I think I had. There we go.
That's a derivative. Okay. So now we'll hit escape. You gotta delete some of that. There you go. Okay, there's your second derivative, right? And that needs to go on here, so -4 sine 2x, what was it? What was the rest of it?
Minus 2 cosine x.
2 cosine x equals 0. Okay, so go ahead and solve that. So we're using the calculator for a lot of this, right? We wouldn't have to use a calculator for those derivatives, but maybe we'd forget to kick out the 2. Or maybe we'd forget a negative, or whatever. Okay, so let the calculator do it. It's fine. Okay, see, he didn't do the vertical bar, so look what happened. He got that N1 stuff. When you see that N1 stuff, you're like, oh, shoot, I forgot I've got to limit this from 0 to pi. So I've got to do vertical bar, 0 less than or equal to x less than or, but just think, when you're doing a solve, it might be good to limit the solve. That's different than when we were using the vertical bar to just plug stuff in. Okay, pi halves is our only possible inflection point. Remember, this is a possible inflection point where the second derivative is 0. What do we need to show it is?
This side of the grid graph.
Number line, right? Sign analysis. We need to put pi halves on here. We can put 0. We can put pi. We can those are easy enough numbers. We probably don't need the calculator for that. Put in a 0. Sine of 0 is 0. Cosine of 0 is 1. So we get -2 there. Put in a pi. Sine of what? 2 pi, that's 0. Cosine of pi, -1 times -2, that'd be +2. So probably don't need the calculator for that. So is it an inflection point? Yes, you would say inflection point, x equals pi halves. Since f double prime changes sign, f changes concavity.
How can it give us exact values that time we solve it?
Great question. I don't know. The magic of the calculator. That's not the question, though. The question wasn't, was there an inflection point? But boy, I did a great job if it would have been, right? That's a beautiful answer if that would have asked for an inflection point, but it didn't. Where's a concave up? Pi halves to pi, not infinity, because we're only looking from 0 to pi, right? So concave up when f double prime is positive. So from pi halves to pi is the answer to the last part. Okay? Man, if you guys could just do what I did, right? This stuff here, that's the quiz, right? I mean, let's talk about the quiz just a little bit, and I'll give you the last half hour to work here. Okay? So, quiz on Tuesday. Probably half. I mean, I was estimating this. Somebody asked whatever year. Somebody asked, well, how much? You know, I don't know. Roughly 1/2 of the quiz is this chart, global max min kind of stuff. Just because there's a lot of points in one of those problems, you get into one of those problems, you can have 6 or 7 or 8 points, with all the different things. Probably won't ask for all that stuff in just one problem, but maybe within a couple of problems. So those points add up pretty quickly. The differential equation stuff. And what did we talk about with differential equation? We talked about being able to verify that something's a solution. We talked about translating into words or from words, right? Translating from words. And then the other one we talked about was the y equals AE to the KT, being able to do something, because that is really the world's most famous differential equation. I mean, most kind of simplistic, basic, useful differential equation is this exponential growth. Y prime equals K times Y. The rate of change is proportional to the amount you have. The more you have, the faster it grows. The less you have, the slower it grows. Okay? It's just a very basic kind of thing. So being able to do something with bank interest, population growth, expect something like that. Okay? And then the rest is just using your formulas and maybe a few antiderivatives as well. So like we haven't done much of that the last few days. Yesterday we did a little bit. We practiced some of those, like doing the derivative of 3 to the x minus 1, right? You got to kick out an ln3, that kind of thing, because of the rule for that. So review those rules and be able to do that. Okay? So that's kind of the idea of what we're looking for. Now, we wrote down those derivative rules the other day, right? A power rule, e to the x, this one, ln x, different logs, sine, cosine. Don't worry about tangent, that one's not going to be on there. The derivative of tangent is secant squared, actually is what the derivative is, but we'll get into that in chapter 3. Okay, and then we talked about chart stuff and global max min, we just got done doing some examples of that the other day. And then this is what we wrote down yesterday, differential equations, an equation that contains derivatives. Here's an example. An initial value problem would be then when you go and you say, okay, and y of 0 is equal to 3, right? You add on an initial condition. So we wrote this yesterday, an equation that contains derivatives. The solution to a differential equation is the original function, y. This would be a simple one. We could just do the antiderivative, right? And that would be the solution. So we talked about that with differential equations. Okay, the 3 types of differential equations. Ones we could just solve, like I just showed you, by doing an antiderivative. We talked about the money or bank interest, that one. And then the ones where we can just verify that something is a solution. Okay, and there you go. All right, so that's kind of where we're at. That's what we want to be able to do on Tuesday. So if you go down to the next line here, the next group of 3, again, just going back into each one of those sections. Let me see, I might add one. On the 2.6 line, add number 10 to that one. To make that 10, 11, 14, and it's 55, right? Yeah, and 50, 55. Okay, so on the 2.6 line, it should be 10, 11, 14, and 55.